So day 2, or day 1 of unit 2, like introduction to derivatives is, I guess, what we would call this. So let's back up a second. Average rate of change, that should look familiar. That was maybe the last thing you saw in here yesterday, right? Because that was the bonus on the test. And the average rate of change, what did you say the average rate of change was? Yeah, just good old like Algebra 1 slope. Because we're going to use slope in a slightly different way soon enough, so that's why I'm calling it like Algebra 1 slope. Sometimes we'll abbreviate it AROC, especially as opposed to what we'll see in a few minutes. It's not AROC. So let's see. How many different ways can we say this? Change in y over change in x. Change in f over change in x. Y2 minus y1 over x2 minus x1. And I guess if we're getting specific with from A to B, then we would say f of B minus f of A all over B minus A. But like all of that's kind of the same thing for slope. Rise over run. Maybe I could have started with that one, like all the way back to that. But all of those mean the same thing. So average rate of change, same thing as Algebra 1 slope. You've done it a million times. Hopefully you've gotten used to calling it average rate of change. Let's just do one of these because it's the same thing. Let's just skip to example 2. Find the average rate of change. Okay, so when you see that, just think that's not really a calculus question. That's an Algebra 1 question. I guess it's not really Algebra 1 when sign is involved. So g of pi over 9 and g of 0, and then we can do y2 minus y1 over x2 minus x1. So sine of 3 pi over 9, that would be the sine of pi over 3. Everybody knows the sine of pi over 3, but Avery especially knows the sine of pi over 3. Yes, she knows it faster than I know it. And then g of 0, so we'll plug 0 in. Sine of 3 times 0, not the sine of 30 because that would be different. So the sine of 0, and Jake knows that the sine of 0 is 0. Okay, so now we're ready to do the slope thing. Y2 minus y1 over x2 minus x1. And hey, if you're feeling good, that's safe stops, right? You're done. But you know that a multiple choice test is probably not going to look like that as an answer choice. So let's keep it, change it, flip it. And by the way, anything after I box a safe stop is also a safe stop and an acceptable answer. So some of you, like, you simplify a little bit because you're like, well, that looks dumb. I can at least get rid of the zeros, and then you stop here. That's okay. Root 3 over 2 times 9 over pi would be 9 root 3 over 2 pi. Again, those are, in the eyes of an AP grader, those are identical answers. So either one is okay. Obviously, multiple choice is probably going to clean it up a little bit. Okay, so that's slope between 2 points. What we would really like to do, though, is get the slope at a point. In fact, let's just go ahead and say that the definition of a derivative is the slope at a point, as in like 1 point. Which is a little bit weird because the slope formula has 2 points, so how are you supposed to find the slope at a point when you've only got 1 point? This is what we did that first week when we did the slope at point A, B, and C on the yellow graphs around the room. But that was just like eyeballing it. Like now we're going to actually do some math to find the slope. And I guess while we're here, let's go ahead and give it its name, or one of its names, instantaneous rate of change. Instantaneous rate of change. As opposed to average rate of change, like across a span, the average rate of change needs 2 points. The instantaneous rate of change, the IROC, you just need 1 point. But there's still this idea of like, well, how am I supposed to take the slope at 1 point when the slope formula has 2 points? And that's what we'll talk about right now. So let's draw kind of a curve like that. It doesn't have to be exactly like that. And let's say we want to find the slope at x. Again, there's no formula to find the slope at a single point yet. What we know is that if we had another point, then we could find at least something close to this slope. So let's come over to a different point over here somewhere. And this may seem like a weird idea now, but it'll make more sense in a minute. Let's go h away from the point we're looking at. Let's go h away. So if I start at x and I go h farther, then what's the x coordinate of this point? X plus h. I started x, I went h further, so now I'm at x plus h. And if I plug that into to the f, I would evaluate f at x plus h. So now I do have 2 points. So now I can find it's still the average rate of change between those 2 points. So that's not really the slope at a point, but it's close. So let's see what that would be. So y2 minus y1 over x2 minus x1, f of x plus h minus f of x. There's our change in y. Our change in our change in x, excuse me. I guess we could write it out. X plus h minus x, which the x's we cancel and we just have h. F of x plus h minus f of x all over h. Okay, that's a lot of letters. But do you see how that's the slope of that? That's called a secant line, by the way, as opposed to a tangent line. That's the slope of a secant line. That's algebra 1. A lot of fancy letters in there, but all of that is algebra 1. Are we good with that so far? Okay, it's not really what we want, though. Like, what we would really like is the slope of a tangent line. Because the slope of that tangent line would be the slope at that point that we're talking about. So what could we do to this picture? And we may have talked briefly about this when we did that. What could we do with h to make our secant line at least closer to the tangent line? What would give us a better... Like right now the secant line is kind of close to the tangent line, so the secant slope is, kind of close to the tangent slope, but it's not super accurate. So what would be a better way to get a better secant slope, or to get that secant slope closer to the tangent slope? What could I do with h? Make it smaller. If I made h smaller, then like if I got it like really, really close, like right down here, then it'd be pretty close. And if I got it like if I zoomed way in and used the magnifying glass and got it like right next to it, it would be right there. So what I want to do is, let's say, for a better slope, get smaller h. Well, yes, but you're still like not exactly there. So what we would like to do to get really close to there is take a limit. So this is where we take what we learned the last unit, the limit stuff, and we want the limit, if we let h go to 0, then our secant line becomes our tangent line, and our average rate of change becomes the instantaneous rate of change. So limit as h goes to 0 of f of x plus h minus f of x all over h. That would be it. Like that's not close, that's it. If we let h go all the way down to 0, that is the instantaneous rate of change. And that is the derivative of f of x. The slope at a point. Slope of a tangent line. And I'm trying to use all of those words because we use all of those words and try to use them. We use them all and hope that you know that they're really the same thing. Instantaneous rate of change, derivative, slope of a tangent line, they all mean the same thing. The symbol for a derivative is f prime. So all of those are the same thing. F prime is the derivative, is the slope of a tangent line, is the instantaneous rate of change, and then there's the fancy formula for it. But don't get, you're going to use this so much that you sort of memorize it by accident. It's one of those things, like you use it, then use it, and use it, and so it just sticks in your brain. But don't forget that where it comes from is just algebra 1 slope. So start with algebra 1 slope, and if we let that denominator go to 0, well then we got not algebra 1 slope, but calculus slope. That's sort of in quotes because that's not really the official name of it, but that's kind of what I call it to separate it from algebra slope. Calculus slope is derivative. Algebra slope is good old y2 minus y1 stuff. Okay, so turn the page and you get the kind of the full picture of it. The definition of a derivative. That one has delta x's in it. But if you just rename h as delta x, then it's the same formula. And depending on which set of books and which set of notes and where you're looking, sometimes it looks like this, and sometimes it has the h in there. So either one, it's the same thing. And again, that's f prime is one of the notations for it. Notation for the derivative of a function. Okay, so we've already called it like 4 or 5 different things. There's also 3 or 4 different ways to write it. We use different notations for the derivative. And it depends on how we're going to use it. They're pretty much interchangeable, so you don't have to worry about, well, is it wrong to use f prime versus dy dx versus y prime? Not really. Like, it would very rarely does it matter because they're interchangeable. The derivative of y with respect to x can be written as, so this is d dx of y, which is the same thing as dy dx. And where that one comes from, like change in y over change in x, that was algebra. But dy over dx, so instead of a delta y, it's a really small difference, like infinitesimally small difference. That's our calculus slope. So algebra slope, delta y over delta x, because you're doing like a chunk of y and a chunk of x. In calculus, we shrink those all the way down to close to nothing, so it's dy over dx. Y prime or f prime, d dx. That, putting it right there means take a derivative. Take the derivative of f of x. So the d dx out front is an operator. It's like, you know what a square root does, you know what a square does, you know what sine does. D dx means take the derivative. Okay, example 1. Given, oh, we're good on time. Find g prime. Okay, so g prime of x, I'm looking back up here at the definition, is the limit. I like using h, but if you want to use delta x, that's fine. It's easier to write h, less work. So that would be g of x plus h minus g of x over h. You probably don't remember it, but in calculus or in pre-cal and in algebra 2, we have you do this algebra step quite a few times. I don't know, does that look familiar to anybody? Okay, I hope so. Like, we did it last week or this week in algebra 2, and they're like, man, that looks crazy. When would we ever use that? I'm like, well, hold on, because in calculus you need it a lot. So hopefully you've got practice on doing that algebra, but we're going to get practice right here. So g of x plus h. That means take the g function and plug in x plus h. By the way, I probably want to be writing smaller than I'm writing, because we're going to have to find g of x plus h. We already know g of x, and then we'll have to plug it into this thing. So let's see, 3 times x plus h squared would be x squared plus 2hx plus h squared minus 2x minus 2h. And then I guess we could distribute the 3. Are we okay with where 2hx comes from? I'm trying not to show every single step because I'm hoping you can FOIL or square x plus h without writing it all out, writing all the terms. But do what you need to do. Okay, so now I've got g of x plus h. Okay, I know the other stuff, so let's start in on our definition of a derivative here. So g prime of x equals the limit as h goes to 0. So remember, that means we're going to shrink the delta x so that we go from an algebra slope to a calculus slope. G of x plus h is all of this stuff. So I'm already running out of room, so let's see if I can write small and fit it in there. 3x squared plus 6hx plus 3h squared minus 2x minus 2h. Made it fit. Minus g of x, which they gave us g of x. So in for g of x goes 3x squared minus 2x. And then all of that is over h. Okay, right now we are at like peak yuckiness. After you plug in all that junk that's a mess, but now things start to look better. Do you see something we could simplify? What could go away? 3x squared minus 3x squared, that'll go away. And the 2x. Careful with the 2x because it looks like it's minus and minus, but distribute the minus sign. The plus 2x cancels the minus 2x. Now, some ambitious people will start canceling h's right here. that's a little dangerous for our first example, so let's just rewrite what's left. 6hx plus 3h squared minus 2h. All of that stuff's left in the top. All over h. I sort of skipped over the when we solve a limit, we're supposed to substitute first, but it's pretty clear if I plug in 0 for h, I'm going to get 0 in the bottom. So I'm trying to simplify that h out of there, and then we'll try substitution. All of those terms have an h, so I can divide the h into each of them, or reduce them all by h. So 6x plus 3h minus 2. I'm still doing the limit as h approaches 0. But now I don't have an h in the bottom anymore, so now I can plug in h equals 0. So wipe out that middle term. I'm only plugging in h is 0, so the 6x, nothing happens to that. Minus 2, nothing happens to that. So my answer is 6x minus 2. And what we just found was our very first derivative. So the slope, oops, I guess that's g, not f. The slope at any point on the graph of g can be found by using 6x minus 2. That would tell us the instantaneous rate of change, the slope at a point, the slope of a tangent line, dy dx, y prime, g prime, like that's all the same stuff. Just trying to hit all those names. So today is one of those days where we get to make use of the stamp. Like the calculus part was really not that bad. The calculus part was plugging in h equals 0 at the very end. Like that's the easy part. All the stuff before that was the algebra part. And if you get this stamp on your test, it's not good news. It means you did the calculus right, but you messed up an algebra step somewhere. Okay, let's try another one. If y equals 1 over x plus 1, write the limit expression for dy dx. Okay, again, that's just another expression for derivative. So dy dx equals limit as h approaches 0 of f of x plus h minus f of x all over h. I think this time I'm going to pass on writing out f of x plus h because it's pretty easy. So I'm just going to replace x with x plus h and just like make the substitute on the fly here, because this one isn't as complicated, at least initially. So 1 over x plus h plus 1 minus 1 over x plus 1 all over h. Yeah, fine. Okay with that? Just replace x with x plus h. Again, on the complicated polynomial, I usually take the time to write it out because there's a lot of algebra in there. This was a pretty simple substitution. Well, the substitution was simple, but the next step, if I plug in h equals 0, I'm going to get 0 over 0. Do you remember how we clear fractions? What do I need to multiply by? A common denominator, which would be like both of those. So it's going to look terrible, but so much stuff cancels that it's going to end up being okay. But initially, it definitely looks pretty bad. So I'm going to multiply by both denominators, multiplying top and bottom by both denominators. That way all my denominators will go away. And hopefully something will cancel and I'll be able to do this. Okay, on the first term, the big chunk cancels and I'm left with x plus 1. On the second term, the x plus 1 cancels and I'm left with x plus h plus 1. Although be careful, because that minus sign needs to go to everything. And then in the denominator, it's a mess, but it's a mess that you leave alone, right? Like don't. It's not even foiling. Don't distribute and then distribute, and you would have a giant mess on your hands. Leave the bottom alone, and we're going to hope that something will cancel here in a minute. It's another stamp problem. The calculus is easy. The algebra is the pain. Okay, so looking in here, the x's cancel. Again, you've got to be careful with that minus sign. The 1s will cancel, because it's 1 minus 1. And if you're careful, the h will cancel, but I'm going to show my work here. I don't want to do too many things at once. It end up canceling too much and losing track of what's what. So what is left in the numerator at this point? Negative h. And in the bottom, there's h, x plus h plus 1, x plus 1. Oh, good. Now I can cancel the h's. So limit as h approaches 0, negative 1 over x plus h plus 1 and x plus 1. Now I can try substituting again. All it does is wipe out that h. So I've got negative 1 over x plus 1 times x plus 1. Negative 1 over x plus 1 squared. That's my dy dx. Right? Like the algebra is the hard part. The calculus really isn't that bad. The calculus steps are write the definition of a derivative and then plug in h equals 0 at the end. Like that's the easy stuff. It's all the algebra in the middle that messes people up. All right, alternative form of a definition. This tells you the slope at a specific point. As opposed to the slope at any point. Like back here on the definition of a derivative. Let's just write that in up here. The slope at any point. So our answers had x's in them because we could plug in any value of x into the example 1 or example 2 and find the slope at any point we wanted to. The alternative form, it's an easier form, but it only tells you the slope at one particular spot. Let's kind of start with the same thing here. And let's say I want to find the slope at A. Let's find the slope at x equals A. It's a similar process to the last one, but instead of using h, we'll just say somewhere over here is x, and f of x. And there's our secant line. So the slope of the secant line is the good old algebra rate of change, or average rate of change. That would be f of x minus f of a over x minus a. Right? No big deal. That's algebra 1. A lot of letters. A rock, M, F, X, A, but that's just the slope of that secant line. But again, we don't really want the slope of a secant line. That's Algebra 1 stuff. We want the slope of a tangent line. So I want A to stay the same spot. I want the slope at A. So what could I do with x to make my secant line get closer to my tangent line? Where could I move x? Closer to A. And if we're moving stuff, well, we may as well take the limit as x approaches A. So let's get x really close to A. And like the concept is the same. We shrink down that delta x, and we get our secant line to get closer to our tangent line. This stuff is still the same. It's still the same formula. It's just there's a limit on it now. This tells us the slope at A. So it's a simpler formula, but it only tells you the slope at a particular point. And so the big question students have is, well, how do I know which one to use? And which one to use is when it tells you at a certain point. Then you use the alternative form. At a certain point, you use the alternative form. So that example 1, f prime at 2. The at 2 means we're going to use the alternative form. If you'll notice, we didn't make a big deal of this because it didn't matter at the time. On the previous example, it was at x, like that's not a certain point. So that's the big definition, or the original definition. If it's at a certain point, you get to use what's kind of an easier formula. Okay, so looking at the formula, let's just plug it in. Limit as x approaches 2, f of x minus f of 2 over x minus 2. It's still the Algebra 1 slope formula. Like, we're doing lots of crazy stuff today, but it's kind of weird that it all goes back to Algebra 1 slope. y2 minus y1 over x2 minus x1. Okay, f of x we know. F of 2, we don't know f of 2, so let's find f of 2. So just plug in 2. Oh, my poor Algebra 2 students with this yesterday on their test. Order of operations, right? Let's square the 2 and then multiply by 2. So 4 times 2 is 8. 16 minus 3 is 13. So limit as x approaches 2. F of x, they gave us. Go back to highlighting the pieces if that helps. So f of x is 2x squared plus 4x minus 3 minus f of 2, which we just found to be 13, all over x minus 2. And I suppose we're supposed to plug in 2, but we can see right away we're going to get 2 in the denominator, so that doesn't really work. Let's see if magically the top would factor. That'd be amazing. Let's see, I can take out a 2. That'll make factoring easier. X squared plus 2x minus 8. That'll factor as well. Into x plus 4. It's kind of the same thing from the factoring on the test. Like, you know something's supposed to cancel, so you kind of have a built-in hint there that probably x minus 2 is a factor of the top, so that it will cancel. Then I can plug in 2. 2 times 2 plus 4. I could leave that as a safe stop, but 6 times 2 is 12. what we found there is the slope of f at x equals 2. And again, that at x equals 2 is what let us do the alternative form. At a certain point means you can use the alternative form. Example 2 and final. If y equals 2x cubed plus 1, write the limit expression for the instantaneous rate of change of y with respect to x. That's a lot of words to say derivative or y prime. But we keep using all the words because we need to make sure you understand that all those words mean derivative. Oh, when x equals 3. That's great. That means we get to use the alternative form. So I need y of 3. 2 times 3 cubed. So that's 27 times 2 is 54. Plus 1 is 55. Okay, so limit as x approaches 3, because that's the point we're worried about. F of x is 2x cubed plus 1. Minus 55 all over x minus 3. All of these problems are rigged to work out. So it looks like, oh no, what are we going to do? And then you start working a little bit. And you're like, wait a minute, I can factor out 2. And then I can factor x cubed minus 27. Let's see, x minus 3, and then same, opposite always positive. Square the first one, multiply the 2 together, square the second one. Magically, the x minus 3's cancel out. Then I can try to plug in 3. I mean, not try, it's going to work. I'm good now. 2 times 3 squared plus 3 times 3 plus 9. I could leave that as a safe stop. 9 plus 9 plus 9 is 27, times 2 is 54. Which is y prime at 3. The slope of the tangent line at x equals 3 is 54. If you wanted the slope somewhere else, this would be the drawback of the alternative form. So you do that work, and then someone says, well, but what about at x equals 4? What is it at x equals 4? Like, I don't know. I got to go do all of this again. So the alternative form is nice, it's short, it's sweet, but it only works at one spot. The original definition works anywhere, so that if you want to know the slope at 2 or 3 or 5, you just plug it in. So it's a little harder, but it gives you a more robust answer. Alternative form is short and sweet, but it only gives you one answer. Alright, that was a lot. That's probably the longest notes day of the unit. Looking ahead. Because we start doing shortcuts on Monday.